Today, mankind has two priority tasks: finding new energy resources while simultaneously controlling global warming. In the quest to reduce CO2 emissions, a new player in the family of carbon compounds has appeared on the scene: methane hydrates. This form of ice is actually flammable, as it contains methane, the same gas used in the kitchens of hundreds of millions of cooks all over planet Earth. These hydrates, present in the oceans and the frozen wastes of the Arctic, represent a much coveted energy resource of vast proportions.
This is one of the biggest reservoirs of methane on Earth.
But the gas contained in the hydrates can also exacerbate global warming.
If this methane were to reach the atmosphere, we wouldn't be able to live on the planet. It would just be too hot.
Since the beginning of the industrial era, methane concentrations in the atmosphere have increased significantly. They have doubled in 250 years. CO2, or carbon dioxide, is the main greenhouse gas responsible for global warming. But methane is a close second. Its spherical molecule, with 1 carbon atom and 4 hydrogen atoms, can store between 20 and 25 times more energy.
Molecule by molecule, methane contributes more to the greenhouse effect, about 20 times more than CO2. We are saved by the fact that there is less methane in the atmosphere than carbon dioxide.
This recent increase in methane levels in the atmosphere is largely a result of human activity. And a considerable share of it comes from the industries of the US, Europe, India, and Southeast Asia. Other significant emissions come from the Siberian wetlands, Indonesia, Africa, and South America, as a result of forest fires and cattle farms. But above all, methane is present in vast quantities at the bottom of the oceans in its solid form, methane hydrates. These methane hydrates represent 40 times the volume of methane gas currently present in the atmosphere. There are high levels of it in the Arctic Ocean, which has gained nearly 3 degrees in temperature over the last 30 years. A few degrees more and the hydrates could melt, leaving the methane to escape, which would in turn exacerbate global warming. In 2008, an English scientific mission set out to the Arctic to ascertain if methane was already escaping from the ocean bed.
At the time before the cruise, no one had ever seen, acoustically or otherwise, any traces of gas coming from the seabed. We were just looking for different kinds of evidence, including gas beneath the seabed using seismic techniques.
In order for methane hydrates to remain in their ice form in the ocean bed, temperatures must be low and pressures strong. These conditions, which maintain the stability of the hydrates, exist at a depth of roughly 400 meters. It is this zone that runs the risk of being modified by the rise in ocean temperature. The mission will therefore focus on this particular zone.
Recognizing that gas could be coming out of the seabed and where the most sensitive zone would be, which is essentially where the hydrate stability field, that zone of where the pressure and the temperature favors it being stable, a solid material. We concentrated our survey with multi-beam echo sounders and also some higher frequency echo sounders, which are usually used for fish finding. And it's actually with that Simrad EK60 that we first started detecting these blooms of bubbles coming out of the seabed. In fact, unexpectedly, we saw one the very first morning of the cruise.
In total, nearly 300 plumes of methane were discovered, many of them located along the critical 400-meter zone. In parallel, a significant number of methane plumes were observed in another part of the Arctic Ocean to the north of Siberia. The conclusions of this research appeared in the journal Science and raised alarm bells in the media. According to climate models, the rapid melting of methane hydrates would severely increase atmospheric temperatures, which could even jeopardize life on Earth. In 2011, the situation worsened as a result of increasing levels of methane and CO2 in the atmosphere. The scientists returned to the Arctic under the leadership of Ian Wright from the National Oceanography Center in England. Several questions needed answering. Are the methane leaks still active? Or are they perhaps increasingly active? And are the methane bubbles reaching the atmosphere?
All of the evidence and all of the climate models suggest that the Arctic is going to warm faster than the rest of the world. So if you're going to warm the atmosphere, then you're going to warm the ocean, then you have a very good chance of warming the seafloor. And then because of you warming the sediments, you're changing the pressure and temperature. And that methane hydrate that was once a solid will turn into a gas. And then that is going into the ocean and potentially into the atmosphere. What we're trying to do on this cruise is get some idea about how the gas is being released, what is the flux of that gas through the seafloor, and critically, is any of that methane getting into the atmosphere? So that's going to be the position.
The pilot of the James Clark Ross positions the boat at the very spot where Graham Westbrook had mapped the methane plumes 3 years earlier. The technicians rapidly deploy equipment to observe and map the Svalbard seabed. And from the very first investigations, they note a series of bubble plumes. Research, in order to better understand these methane leaks, can now begin in earnest.
We are now at a water depth of 372 meters. We can see a continuous stream of bubbles coming from the seafloor. Yep. We are doing two things. The first is to measure the rate at which the bubbles rise through the water column, and the second is to measure the bubble size so we can work out the bubble size and the velocity, on a frame-by-frame basis. So using the visual information and the acoustic information from one flare, we can then make some estimate of the methane flux from the seafloor.
Using an echo sounder, Ian Wright hopes to find out whether or not the methane bubble plumes are reaching the surface.
This looks really interesting. Here we have a whole series of acoustic plumes. Here's the seafloor at just shallower than 400 meters. So we can see 1, 2, 3, 4, 5 bubble plumes, and these are representing methane gas coming up into the water column. Is that the highest one compared to the biggest one that you saw this morning? Yeah, okay. This one is coming up to at least 200 meters water depth, and maybe faint traces of it getting up to 100 meters.
A critical piece of information, coupled with a sense of relief. The bubble plumes observed at the upper limit of the stability zone of hydrates are not reaching the ocean surface. As the bubbles are not reaching the surface, the methane cannot reach the atmosphere. But what becomes of it then? How does it disappear? Rachel James will attempt to find out by analyzing the chemical composition of the water above a plume of methane gas bubbles.
This image shows the sea floor here, and this is the seawater, or what we call the water column. So the ship is sitting here. What we can see here is a plume of gas bubbles rising all the way from the sea floor, a few hundred meters upwards. And what we're going to do is we're going to take a series of water samples at different depths above the sea floor and measure the methane concentration in them.
349.
The methane doesn't just get into seawater and stay as methane in gas bubbles. The methane will start to dissolve in the seawater, and it will also react with the oxygen in the seawater and be chemically transformed into carbon dioxide.
Bacteria in the water are causing this providential transformation of methane. These bacteria are such avid consumers of methane, they could devour all traces of it contained in the samples.
What I'm doing now is I'm killing all of the bacteria in this sample with a very strong poison. If we were to leave these bags without any poison in them, what would happen is the bacteria in the bags would eat all the methane. We don't want that to happen because then our readings would be too low.
Without the actions of the methane-eating bacteria, these bubbles would reach the atmosphere. But what if the hydrates started melting on a massive scale? If this were to happen, could the bacteria still manage to consume the vast quantities of methane released into the ocean? If it were not for one of the oil industry's most tragic accidents, this question would probably still go unanswered. On the 20th of April, 2010, an explosion started a fire on the Deepwater Horizon platform in the Gulf of Mexico. 2 days later, the huge structure sank as U.S. Coast Guards looked on, powerless. 1,500 meters from the seabed, the head of the damaged well started to leak massive quantities of hydrocarbons. Oil, of course, but mostly gas, and mainly methane. A major ecological catastrophe threatened the Gulf of Mexico's exceptional fauna.
The total environmental release of methane was approximately 200,000 metric tons that became then dissolved in these layers. This was the largest release of methane that was ever observed in a very, very isolated area.
For John Kessler, an expert on methane in the ocean, and his colleague David Valentine, a microbiologist, the accident provided a unique opportunity to observe the ocean's natural reaction to the vast injection of methane.
What happens when the ocean has a large injection of methane, be that injection from a natural process or a man-made one? How does the ocean respond? Is there the capacity for the microbiology to handle some of this methane, or will it eventually propagate to different areas of the ocean, potentially even the atmosphere?
The catastrophic conditions did not prevent Kessler and Valentine from pursuing their investigation. Would these 200,000 tons of methane dissolve in the ocean or reach the atmosphere?
We measured the surface water concentration of methane with very high resolution, from the start of the cruise all the way till we got back into port at the end of it. To probe the deeper waters is a slightly more complex operation. We need to be able to send sampling bottles all the way down to be able to collect a profile of water from that sea floor all the way up to the sea surface.
After 10 days and nights of analyses, Kessler and Valentine made the unfortunate observation that the enormous quantity of methane gas was stagnating in the ocean. At a depth of about 1,000 meters, with concentrations of 10,000 to 100,000 times above the norm.
That methane that was released from this disaster that was isolated in these deep plumes at roughly 1,000 meters depth below the sea surface would remain in these locations for years, if not a decade or more.
Very bad news. the methane-eating bacteria did not seem to be attacking the vast quantities of gas. This meant the water could become toxic for marine life. Alarmed at the situation, the U.S. National Science Foundation immediately funded a new expedition.
We went back out at the end of the summer and the beginning of the fall to study that longer-term evolution of that deep methane plume.
But a very big surprise was in store. The gigantic layer of methane could not be found. In the space of barely 2 months, it had totally disappeared.
Myself and my colleague, David Valentine, started to look at each other and say, where did this methane go? And it was actually him who first said, I think we need to consider the possibility that it was consumed by microorganisms. At first, I was a little skeptical of this.
How could the bacteria have devoured so much methane in so little time?
When methane goes out of the sediments into the majority of ocean waters, there is plenty of oxygen around. And then the consumption of that methane occurs by bacteria. This is the aerobic oxidation of methane that uses oxygen.
Kessler and Valentine were able to reconstruct the scenario of the vanishing methane using measurements of oxygen levels in the water carried out during the summer.
From that, we can see exactly how this oxygen loss, which is related to this microbial feast, changed in both space and time, and ultimately, it helps to support our original hypothesis that methane was consumed in this time period.
Never before had a bacterial reaction been observed on such a large scale. Kessler and Valentine's results had initially left many of their colleagues skeptical, but their conclusions were now confirmed.
We all now going back and trying to get a much more fundamental understanding on how this process actually functions and the inherent capabilities of these organisms.
The methane-eating bacteria had eliminated most of the gas released by the platform accident. So they should be able to do the same thing if ever the melting of hydrates caused large quantities of methane to be released into the ocean. But there's a flip side to the observation that methane disappears in water. When bacteria consume methane, they reject carbon dioxide, which increases the acidification of oceans. At a laboratory in the Mediterranean town of Villefranche-sur-Mer, Jean-Pierre Gattuso is leading research into the consequences of this modern-day plight of the oceans. Acidification is depriving numerous marine animals of a key element they need for development, carbonates.
Carbonates is just a big word for something very simple. It's an essential element needed to make calcium. Calcium is calcium carbonate. Coral, oysters, mussels, all need this basic building brick in order to make their skeletons and shells. This brick becomes increasingly scarce as acidity rises.
Via the experiments carried out in the Bay of Villefranche, scientists are seeking to find out how marine organisms, from the very smallest to the very largest, react to the rising acidification of the oceans. Jean-Pierre Gattuso recently took part in studies in the Arctic Ocean, where acidification is in a more advanced state than elsewhere.
Other organisms in seawater, pteropods, are also calcareous and also need carbonate ions to make their shells. Pteropods are small pelagic mollusks, like sea snails, and they are abundant in the Arctic. It has been demonstrated that these pteropods will very probably disappear from a large part of the Arctic by the end of the century, as they can no longer build their shells.
Are these sea snails the forewarning signs of a drastic change in the ecosystem of the Arctic, to which methane hydrates are largely contributing?
In the Arctic, the absorption of CO2 by the atmosphere occurs alongside ocean floor production of CO2. This dual CO2 production creates a sandwich effect, leading to a possible doubling of acidification in the Arctic by the end of the century as a result of destabilization of methane.
Back on board the James Clark Ross, the scientists are getting ready to take sediment samples in a zone where methane injection has been located. when they noticed the shells of sea animals that appeared to have died.
Here we are trying to sample the sea floor with a new attachment to HIBIS, which is a TV grab. And what we want to do is recover some of these dead shells to understand the possible relationship between methane coming from the sea floor and these animals dying. Ian speaking, we have a sample, so we're coming straight to the surface right now. And that will be the last dive.
Yeah. Could these animals be the victims of increasing acidification in Arctic waters? To find out, the sediments must be closely examined. The surface of the sediment is covered with layers of bacteria, irrefutable proof of the presence of methane.
That smells very fresh.
The strong smell of rotten eggs, so characteristic of organic degradation, does nothing to deter Rachel from examining the sample.
This is a bivalve that I've recovered from within these sediments, and what's really unusual about it is that the surface, which should normally be really smooth and shiny, looks terrible. And it suggests to me that these black sediments here are really acidic, and that acid is etching and eating away at the surface of that shell. So there's nothing that I can see living in these sediments, and that's because the methane is using up the oxygen in the sediments. So these organisms simply can't live, they can't survive. But what I can't see are the bacteria that are likely to be living in here. Millions and billions of them that will be using the methane and also the hydrogen sulfide in these sediments as a source of energy.
A rise in the number of methane hydrate leaks will acidify the ocean floor and endanger the lives of certain sea animals. However, in the sediment, Rachel notes the presence of numerous other methane-consuming bacteria that do not use oxygen. Are these other bacteria playing a protective role by preventing methane from entering the water column? Taking a sample of the first few meters of sediment will provide the scientists with further information on these species of bacteria, which for now remain rather a mystery to them.
The reason we're looking at mud is because, of course, the methane that moves through the sediments, it's chemically reactive. It doesn't just simply pass straight through the sediments. There are whole huge consortia of bacteria and archaea living within those sediments that love methane. They absolutely adore it, and they'll try to consume that. One thing we want to know is, what are the optimal conditions for those bacteria to grow?
Beth Orcutt is one scientist who might be able to answer Rachel's questions. She's about to discover whether these bacteria play an important role in methane degradation. Just a few kilometers from the University of Aarhus, she is preparing to test a new system of observing bacteria in their natural milieu.
In areas where there's a lot of organic matter settling to the seafloor, methane appearing at about 50 centimeters below the seafloor. And again, this methane is being generated by organisms living in the sediment. They're degrading the organic matter and converting it into methane. And above where that's happening, there's actually some organisms that are living in the sediment that can also eat methane. And so there's a coupling happening between making methane and consuming the methane. And these processes are all controlled by the bacteria living in the sediment. And part of what we want to do is study that process in the actual seabed.
The aim of this research project is to discover what is regulating the life of these bacterial communities and how it benefits the climate. But the task is a difficult one, as the scientists are dealing with life forms they know very little about.
That we really don't understand the separation between the organisms that can make methane and that eat methane, because genetically they're not that different. So it's actually biochemically a very intriguing question. How could an organism possibly switch from eating something to making it? That would be the same as saying we breathe oxygen and then we also make oxygen. That would be really weird.
For a long time, the consumption of methane by bacteria in oxygen-free environments has been considered to be of limited interest. As little as a decade ago, microbiologists had no idea how decisive the phenomenon could be for our climate. Antje Boetius, a renowned specialist in oceanography microbiology, now believes these microorganisms play a major role.
For over half the history of the Earth, there was no oxygen in the atmosphere. Yet right from the start, large quantities of methane were present. It is very possible that these microorganisms could have formed the first biofilms, generated biodiversity, and brought energy into the food chain. That's what makes them so important.
These bacteria, which can live in sediment thanks to methane, are highly precious organisms for the health of oceans and the atmosphere. Their ability to consume methane without using oxygen is a mystery that Antje Boetius has set out to solve. She has discovered that two types of microorganisms combine to consume methane.
Observing this cooperation between two different types of microorganism has taken our research further. Through the microscope, we have observed aggregates of cells of a particular life form, monocellular organisms called archaea, and bacteria. In this fabulous image, we can clearly see the very dense agglomeration of two types of microorganisms. The archaea in red, and in green, other much smaller cells, bacteria. This really does signify that they need to exchange energy and that they need each other to oxidize methane.
The mysterious cooperation between these two species of microorganisms seems to be the only way they could consume methane in an oxygen-free environment.
Very little methane leaves the ocean. For a long time we wondered why. Today we know that these microorganisms manage to transform the methane on the seabed, almost in its entirety. We must therefore concede that these microorganisms have a strong effect on the Earth's climate.
Without this cooperation between archaea and bacteria, methane, which migrates from the deep layers of sediment, would threaten the balance of the oceans and perhaps even our climate.
Together, this association of microorganisms devours 80 to 90% of all methane present in the oceans. If this methane were to reach the atmosphere, we humans could not survive on Earth. It would just be far too hot.
So fortunately, the majority of the methane that threatens to reach the atmosphere is consumed by bacteria, either in the ocean sediments or in the water column. Our investigation continues among the ice plains of Siberia, where a second source of methane could also threaten the atmosphere. Permafrost, which extends over nearly a quarter of the Northern Hemisphere's landmass, contains a vast quantity of organic matter that could be transformed into methane by bacteria. The soil is considered as permafrost when its temperature has been below zero for at least 2 consecutive years. Certain zones of permafrost are over a kilometer thick and have been frozen for over 10,000 years. Could the vast quantities of organic matter they contain become a daunting, ticking climate bomb?
Today it is minus 39 degrees in Yakutsk. But this is a lot milder than the temperature observed at the same period 10 or 20 years ago. Average temperatures for January have increased by 10 degrees.
With an increase of over 2 degrees in average temperatures over the last 30 years, the state of the permafrost is causing concern. The vast quantities of organic matter frozen during the Ice Age, which ended 10,000 years ago, could now decompose, releasing vast quantities of methane.
We are on our way to an internationally renowned research station, Spasskaya Pad.
During the winter months, just one weather station in the whole of Siberia continues to operate 24 hours a day, in the heart of the taiga. The area of permafrost is being monitored closely.
In the space of 13 days, 15,000 pieces of data have been collected. The data comes from the tower. A total of 72 parameters are processed. This data is used to create temperature graphs for the air and the soil. It is central to climate change analysis. $7.84.
Scientists are carefully monitoring the temperature of the Earth's upper layer, a layer that is said to be active because it thaws every summer. Global warming is threatening to increase this active layer and to expose more organic matter to degradation by bacteria. But Trofim Maximov believes this is a relative danger.
Melting is a very long and complex process that takes place over 50 to 100,000 years. For an immense structure like permafrost to melt, a vast quantity of energy would be needed.
Permafrost does not melt overnight. But a visit to an industrial installation in the Arctic Circle confirms the harsh realities of global warming. Here, in order to carry out sustainable construction, the first few meters of permafrost now need to be actively cooled.
Initially, this site contained thawed ground at around 0 degrees and permafrost at minus 0.5 or minus 1 degree. Behind me are the heat exchangers for the systems of permafrost cooling and freezing, and the foundations of this gas compression station. They lower the temperature of the permafrost to a level that guarantees the stability of the foundations.
In this region, the increase in precipitation from global warming has caused an impressive number of lakes to form. Each lake, in turn, furthers the melting of the permafrost, exposing more areas of organic matter, which inevitably increase methane production. The climate conditions of the Arctic, where phases of freezing follow phases of thawing, cause the formation of another visually spectacular type of lake, polygon lakes. The strong seasonal thermal variations cause the soil to crack. Water filters through these cracks, enlarging them and accelerating degradation of the active layer. Scientists are currently observing a clear proliferation of polygon lakes. These lakes also favor the decomposition of vegetal or animal remains that have been stored in the ice for thousands of years. Measurements of greenhouse gas emissions carried out in the tundra show a clear rise in methane levels, a trend that is set to increase, according to climate models. But ecosystems are so complex that it is very difficult to predict all the effects this warming will have.
The interdisciplinary research on greenhouse gases that we are carrying out at this station has enabled us to obtain very interesting results. It has shown that the Russian forest ecosystems are absorbing greenhouse gases, mainly carbon dioxide and methane.
With a surface area 6 to 7 times greater than the methane-emitting zones, the Siberian forests, which are taking advantage of global warming to develop, are for now offsetting the rise in methane emissions. But the permafrost also contains large quantities of methane hydrates that could be destabilized by warming. In the Canadian Great North, which is also part of the permafrost zone, several programs monitoring methane emissions are in operation. Scott Dallimore, a geologist with Natural Resources Canada, is working on one such program.
So the flight time from Inuvik is about 45 minutes, more or less due north, right to the edge of the Mackenzie Delta. And the weather today looks pretty good.
Scott is traveling to a remote area of the Mackenzie Delta to implement a long-term observation technique for a natural methane leak. He will also attempt to determine the origin of the methane. Is it coming from organic decomposition or from methane hydrates?
This is a location where natural gas is coming through to the surface beneath a river channel. It was first discovered in '62. It was also known by the local people who would use it as a source of drinking water in the winter.
Like this,
This is a hydrophone logging unit. There's a high-resolution underwater microphone, a hydrophone, and then a data logger system and a bunch of batteries. It'll continuously record sound at the bottom of this channel here, where we have a gas seep coming to the surface. You okay, everybody? The flux of methane that we observe at the surface is most likely related to processes that were generated many thousands of years ago. So there's a long time lag between the change at the surface and the signal penetrating the ground and creating a process that can, for instance, destabilize gas hydrates or change the permafrost conditions and allow gas to migrate to the surface. The question, however, is how much gas is currently being released by these processes to the surface. We need to quantify that because it's an important input parameter to our predictions of future.
The methane leak proves to have an irregular flux, and the origin of the gas is linked to the dissociation of probably ancient methane hydrates, as Scott Dallimore suspected. Whether in the ocean or in the permafrost, methane leaks really do exist, and in some cases, the methane is reaching the atmosphere. But scientific research has shown that natural mechanisms seem to be able to degrade a large part of this methane, thereby limiting the extent of these leaks. Our planet's past, in which cycles of warming and cooling followed each other, can help us to understand the future evolutions of methane. Paleoclimatologists like Jérôme Chapelaz are seeking to understand the methane variations of the past by analyzing the gas bubbles they find in ancient polar ice.
This ice contains samples of the atmosphere in small bubbles. Our work consists of extracting these small bubbles to look at the quantities of greenhouse gas inside and to study the evolution of that greenhouse gas over time. Up until now, our way of working consisted of taking an isolated sample of gas, extracting the gas, and analyzing it via a technique that we call gas chromatography. What's new, and what we've been able to implement here thanks to colleagues who are laser physics experts, is that we've developed an instrument that can measure the methane in air bubbles that are continuously escaping from the gas sample on site.
We travel to the north of Greenland, to a glaciology laboratory that is isolated from the rest of the world. Scientists from 13 countries gather here every summer to reconstitute the past of our planet's climate and to understand how methane hydrates behave during the periods of global warming of the last 30,000 years.
Climate change sounds for many people like science fiction, but I think what is important about this project is that we can actually go back to the future. We can make measurements and sort of make comparisons and see, well, how was it way back? And then we can then sort of make evaluations of how a 2-degree world would actually look like.
At the Nîmes research station, the real star is the drilling machine, capable of boring through over nearly 2,500 meters of ice. Without it, there would be no time travel. The new laser technique that Jérôme Chapelaz's team is using will prove highly efficient in detailing past methane fluctuations in the atmosphere.
The rise in methane that we have observed in the gas samples happened after the period of global warming. It is not the trigger, but a response to climate change.
So methane accompanies phases of warming rather than causing them. 11,500 years ago, during the last great ice thaw, methane concentration levels in the atmosphere leapt by 50%. One American paleoclimatologist, Vasily Petrenko, wanted to find out where this extra methane came from. Was it of land origin, or did it come from the seabed?
I'm trying to understand why methane rose and where all this extra methane was coming from, because of course now we're experiencing another large global warming, and we need to understand, in addition to anthropogenic methane sources, how the natural methane sources are going to respond.
The first step involves traveling to a glacier in Antarctica to collect ice that is 11,500 years old.
Luckily, you can get old ice coming up to the surface at the margins of the ice sheets, and that's because ice that gets deposited near the center of an ice sheet will flow mostly downwards at first, but then it flows along the bed of the ice sheet and has to come up somewhere along the margin. And the ice that emerges closest to the margin is typically the oldest.
This method facilitates collection of a ton of ice, which must then be melted in order to collect just 2 cubic centimeters of 11,500-year-old gas. From this gas, 20 micrograms of carbon are extracted, which contains the information Petrenko is looking for.
If the carbon has recently come essentially from the Earth's surface, it will have some carbon-14. Whereas if this carbon has been sitting in some reservoir for a really long time, such as methane hydrates in ocean sediments, then this carbon will not have any carbon-14.
Minute examination of this carbon reveals that it contains a rather large quantity of carbon-14.
We plotted these data on the graph that showed the methane increase as well as what carbon-14 is expected to look like under a wetland scenario and under a methane hydrate scenario. The results suggested that this particular large methane increase at 11,500 years ago really was due to increased methane emissions from wetlands, that methane hydrates did not have much of a role.
Scenarios of sudden climate warming, in which methane hydrates were thought to have played a major role, are therefore judged to be rather implausible.
Really, really good.
And yet, all current research on the methane cycle must be pursued, because with global warming, emissions of the gas will continue to increase. It is difficult to control emissions of natural origin, which are increasing very slowly. But emissions of human origin, which in just 250 years have caused a doubling of methane in the atmosphere, could be reduced. And in particular, those emissions from the oil and gas industries, which release large quantities of gas through negligence during the production and transport of hydrocarbons. Controlling our methane emissions is clearly the surest way to avoid new climate nightmares. But methane hydrates also represent the promise of vast energy resources for mankind, so desperately in need of an energy transition.